Welcome to G Fun Facts Online. Today, we are going to conduct a thought experiment that takes us into the very fabric of the material world. I want you to imagine shrinking yourself down to the size of a bacterium. In this realm, the world becomes a strange and hostile place. The rules of gravity that govern our daily lives fade away, replaced by the sticky, overwhelming forces of surface tension and van der Waals interactions. In this alien landscape, our traditional manufacturing tools are useless. Drills, lathes, and molds are simply too clumsy, too brutal, and far too large. Yet, it is precisely here, in this sub-micron realm, that the future of medicine, computing, and materials science is being forged. For decades, the ability to build complex, three-dimensional structures at this scale was just a dream. We could etch flat patterns onto silicon chips, but true 3D manufacturing, the ability to build intricate lattice towers, functional microturbines, or scaffolds for living cells, remained out of reach. That is, until the mastery of a phenomenon known as Two-Photon Polymerization, or 2PP. This is not merely 3D printing for small things. It is a fundamental rethinking of how we manipulate matter with light. By harnessing the non-linear quantum optics of femtosecond lasers, engineers can now solidify liquid resin at a resolution that defies the traditional diffraction limits of light itself. We are no longer just printing, we are sculpting with photons, creating architectures so fine that they are invisible to the naked eye, but strong enough to change the world. To understand why 2PP is such a revolutionary leap, we first need to appreciate the limitations of the tools that came before it. Traditional stereolithography, which is essentially the grandfather of light-based 3D printing, works on a principle of one-photon absorption. Imagine a laser beam of ultraviolet light tracing a shape on the surface of a vat of liquid resin. Wherever that beam hits, the resin absorbs a photon, a chemical bond breaks, and the liquid turns into a solid polymer. The problem with this method is that the absorption happens everywhere the light touches. As the laser beam travels through the resin, it cures the material all along its path, much like a flashlight beam freezing water into ice. This limits you to building layer by layer, from the bottom up, with significant constraints on geometry and resolution. Two-photon polymerization changes the game by exploiting a loophole in quantum mechanics. In 1931, Nobel laureate Maria Goeppert-Mayer predicted a phenomenon that seemed purely theoretical at the time. She theorized that an atom or molecule could absorb two photons simultaneously in a single quantum event, provided they arrived within a fraction of a femtosecond of each other. That is 1/4,000,000th of a second. The combined energy of these two less energetic photons would equal the energy of the one high-energy photon needed to trigger a chemical reaction. This simultaneity is the key. In a 2PP system, the resin is transparent to the near-infrared laser used. When the laser beam passes through the resin, nothing happens because the photons are too weak individually to trigger polymerization. The light simply passes through the liquid, like sunlight through a window. However, researchers use a high numerical aperture lens to focus this laser beam into a vanishingly small point. At this focal point, and only at this focal point, the density of photons becomes astronomically high. For a fleeting instant, the probability of a molecule getting hit by two photons at the exact same time skyrockets. The resin molecule absorbs the combined energy, becomes excited, and initiates the polymerization reaction. The result is magical. Instead of a beam that hardens everything in its path, you have a voxel, or a volumetric pixel, of solid plastic that forms floating deep inside the liquid resin. The material above and below the focal point remains liquid. This spatial confinement allows for true 3D writing. You are not bound to layers. You can move the laser focus in any direction, up, down, left, right, or diagonal, drawing free-form structures inside the volume of the material. It is akin to moving a pen through the air and having the ink solidify instantly in 3D space. Furthermore, because the two-photon absorption effect depends on the square of the light intensity, the reaction volume is even smaller than the focused spot of the laser itself. By carefully controlling the laser power near the threshold of polymerization, engineers can create features as small as 100 nanometers, which is hundreds of times thinner than a human hair. Now let us look at the machinery that makes this possible. The hardware required to orchestrate this quantum dance is a marvel of modern engineering, having evolved from optical tables in university basements to sleek, industrial-grade desktop machines in 2024 and 2025. The engine of a 2PP system is the femtosecond laser. These devices emit pulses of light that last only 100 to 200 femtoseconds. To visualize this timescale, a femtosecond is to a second what a second is to about 31.7 million years. These ultra-short pulses are necessary to pack enough photons into a brief moment to trigger the two-photon effect without boiling the resin. If you used a continuous wave laser with the same average power, you would simply heat up the liquid. The pulsed nature allows for peak intensities of terawatts per square centimeter, intensities usually found in nuclear explosions, but only for such a short time that the material does not burn, it just chemically reacts. Directing this laser focus requires extreme precision. Early systems moved the sample stage using piezoelectric motors, which are precise but slow. Modern systems, such as those developed by leaders like Nanoscribe and UpNano, utilize a hybrid approach. High-speed galvanometer mirrors deflect the laser beam to scan the fast axes, writing a slice of the structure at lightning speeds, while a piezo stage moves the sample in the vertical axis to position the writing volume. In 2024 and 2025, a major leap occurred in writing speeds. New holographic multifoci techniques have shattered previous limits. By passing the laser beam through a spatial light modulator, the single beam is split into a hologram of dozens, or even hundreds of focal points. These ghost pens write simultaneously, increasing throughput by orders of magnitude. A recent breakthrough reported in Nano Letters in 2024 demonstrated a system writing at over 149 million voxels per second, creating complex millimeter-scale structures in seconds rather than hours. Software has become just as critical as hardware. Writing at the nanoscale introduces challenges that do not exist in macro 3D printing. As the resin polymerizes, it shrinks slightly, which can cause delicate nanostructures to warp or collapse. By 2026, smart slicing software has become the standard. These programs use deep reinforcement learning to predict how the material will behave during the print. They automatically adjust the laser power, writing speed, and pathing to compensate for shrinkage and optical aberrations. For instance, when writing deep inside a thick layer of resin, the refractive index mismatch can distort the laser focus, making it look like a comet rather than a sphere. New AI-driven aberration correction modules dynamically alter the wavefront of the laser to keep the focus sharp, regardless of how deep into the material the printer is working. This has effectively doubled the printable height of many microstructures. The ink used in 2PP is just as sophisticated as the printer. Initially, researchers used standard photoresists from the semiconductor industry, which were rigid and brittle. Today, the palette of materials is vast and functional. One of the most significant trends of the 2024 to 2026 period has been the explosion of biocompatible resins. Standard industrial resins are often cytotoxic, meaning they kill cells. For biomedical applications, the material must be friendly to life. New hydrogel-based resins, such as modified gelatin methacryloyl and hyaluronic acid derivatives, allow for the printing of scaffolds that mimic the softness and water content of natural tissue. These materials are tunable, meaning their stiffness can be adjusted to match bone, cartilage, or brain tissue. A breakthrough in late 2024 saw the introduction of UpNano Green, a system utilizing a 515 nanometer green laser instead of the traditional 780 nanometer infrared. This wavelength shift was crucial because it allowed the polymerization of new classes of biomaterials that were previously transparent or unresponsive to infrared light. This opened the door to printing with proteins and enzymes directly, without denaturing them. It is not just about structure, it is about function. We can now print piezoelectric resins, materials that generate electricity when squeezed. This allows for the creation of microscopic sensors and energy harvesters that power themselves from the vibrations of blood flow or sound waves. While printing pure metal via 2PP is difficult, conductive polymers allow for the direct writing of electrical circuits at the microscale. We also see shape memory polymers, enabling 4D printing. These materials change shape when exposed to heat, pH changes, or light. A 2025 study demonstrated 4D printed microgrippers that are printed in an open state but snap shut when introduced to a specific acidic environment, like a tumor microenvironment, to release a drug payload. The killer application for 2PP has undoubtedly been in medicine. The ability to structure matter at the same scale as cells and subcellular components has bridged the gap between biology and engineering. Consider organ-on-a-chip devices. These are microfluidic chips that simulate the activities of human organs. They contain tiny channels lined with living human cells. The challenge has always been recreating the complex, fractal-like network of blood vessels that keeps real organs alive. Traditional manufacturing cannot make 3D microcapillaries. 2PP can. In 2025, researchers at Missouri S&T unveiled a one-pot resin method that allows for the rapid printing of highly branched, porous blood vessel networks inside a chip. By flowing nutrients through these 2PP printed capillaries, they kept thick liver tissue constructs alive for weeks, allowing for drug toxicity testing that is far more accurate than animal models. Perhaps the most sci-fi application is the micro-robot. These are not mechanical droids with gears and batteries, but chemically or magnetically driven architectures. In 2025, a team created light-driven micro-robots using 2PP. These helical swimmers, coated with a thin layer of metal, can be steered through fluids using external magnetic fields. But the breakthrough was the cargo handling. Using laser-induced convection currents, which involves controlled heating of the water around the bot, these robots could trap a single drug molecule or cell, transport it to a specific location in a petri dish, and release it. Imagine a swarm of thousands of these 2PP printed bots injected into the bloodstream, guided magnetically to a blood clot, and mechanically drilling through it to restore flow. This is no longer pure fantasy. The prototypes are swimming in labs today. 2PP is also revolutionizing neural interfaces. The brain does not like hard metal electrodes. When you stick a silicon probe into the cortex, the brain reacts with inflammation, forming a scar that blocks the signal. 2PP allows for the fabrication of fluffy electrodes, conductive hydrogel towers that look like microscopic moss. These structures match the mechanical impedance of brain tissue, allowing neurons to grow into the electrode rather than retreating from it. This could lead to brain-machine interfaces that last for decades rather than months. While medicine repairs the body, 2PP is also upgrading the brain of our digital infrastructure. As Moore's law slows down, the bottleneck in computing is no longer how fast the transistor switches, but how fast data moves between chips. Copper wires are too slow and generate too much heat. The future is optical interconnects, moving data with light. Connecting two optical chips is notoriously difficult because they must be aligned with sub-micron precision. 2PP offers a solution called the photonic wire bond. Instead of aligning the chips perfectly, you simply glue them down roughly in place. Then, a 2PP machine scans the position of both chips and 3D prints a polymer waveguide, a bridge, that connects the optical port of one chip to the other. The shape of the bridge is calculated on the fly to route the light perfectly around corners and over steps. This technology is now entering mass production, enabling the high-bandwidth transceivers needed for AI data centers. In the quantum realm, 2PP is enabling the impossible. A 2025 breakthrough out of China showcased a photonic quantum chip with over 1,000 components integrated onto a lithium niobate wafer. 2PP was used to create 3D coupling structures that allowed light to enter and exit the chip with almost zero loss, a critical requirement for preserving fragile quantum states. Furthermore, 2PP is the primary tool for creating metamaterials, materials with structures that manipulate electromagnetic waves in unnatural ways. Researchers have printed invisibility cloaks for infrared light, lattices that bend light around an object so it casts no shadow. While still microscopic, these materials are paving the way for flat lenses that could replace the bulky glass in your smartphone camera with a wafer-thin diffractive optic. If 2PP is so powerful, why isn't everything manufactured this way? The primary hurdles are speed and cost. Writing point by point is inherently slow. Printing a cubic centimeter of material with 100 nanometer resolution would take years with a single beam system. The industry response in 2024 through 2026 has been parallelization. We are seeing the shift from single-pen to thousand-pen systems. The use of diffractive optical elements and high-speed spatial light modulators means that a single laser source can drive a massive array of focal points. The NanoPro service launched by UpNano serves as a testament to this, offering the first industrial-scale production of 2PP microparts, churning out batches of thousands of identical micro-lenses or nozzles in hours. Then there is the cost of light. Femtosecond lasers are expensive, often costing tens of thousands of dollars. However, a 2024 study introduced a two-color printing method. By combining a cheap, low-power continuous laser to prime the resin with a lower-power femtosecond laser to trigger the reaction, researchers reduced the cost of the required laser source by 50%. As fiber-based femtosecond lasers become more common, driven by the eye surgery and display manufacturing markets, the cost of 2PP machines is expected to drop significantly. As we look toward 2030, Two-Photon Polymerization is poised to leave the clean room. We will likely see roll-to-roll 2PP systems, where a flexible film is continuously spooled under a multi-beam writing head, printing microtextures that make solar panels more efficient, or shark skin surfaces that prevent bacteria growth on hospital catheters. We will see the integration of 2PP with other manufacturing methods, hybrid printers that use inkjet heads to lay down the bulk material, and 2PP lasers to add the high-resolution features are already in development. Imagine a contact lens printed in seconds, with a 2PP laser writing a custom waveguide display into the lens material for augmented reality applications. In the end, two-photon polymerization represents the ultimate democratization of nanotechnology. It is a tool that allows a designer to sketch a machine the size of a dust mite and hold it, or at least see it under a microscope, minutes later. It is the bridge between the digital code of our imagination and the physical reality of the very small. And in that small space, the biggest revolutions are waiting to happen. Thank you for listening to G Fun Facts Online.